Hey yo, this is my video solution assignment for quantum mechanics, and I'm doing problem 2.8. So it gives you this wave function at t equals 0. It equals a constant c times in parentheses 4 minus x squared, and that's all in the region where x is in between -2 and 2, and it equals 0 everywhere else. So this is looking a lot like a infinite square well. And there's five parts to this question. To this problem. Question one is to normalize the wave function. So to normalize it, you use this formula, or the definition of normalizing is you have the inner product of the wave function with itself, and it equals 1. That's the definition of normalize. But we're working with wave functions, so to express that from Dirac notation to wave function notation, we use the integral over all space. So from negative infinity to infinity of the wave function squared in and then of dx, and that equals 1. So that's how you basically say normalization definition in wave function notation. So then you pretty much just plug this wave function into that formula. And here I actually changed the bounds from -2 to 2 because just like we said, it's 0 everywhere else. So we could sub that in instead of using infinity. So you just plug this in, and then you can take, and then we're solving for c, but then you can take that out of the integral c squared because it's a constant. And then I just solve the integral using an integral calculator, and you get 34.1333 to infinity. And then remember that's equal to 1 because it's normalization. So then that's what I have over here, equals 1. And then you just use algebra to solve for c. And then you get the square root of 1 over 34.1333. And that just equals 0.171 to 3 decimal places. Moving on to question 2. So that's the answer to question 1, but question 2 now asks for the expectation value of x. And then to solve for that, we know the formula for expectation value as you find it in the textbook. You do the inner product of the wave function again, but you kind of just squish x in between there. And remember, that's Dirac notation. So to express that in wave function notation, we use the integral from -infinity to infinity again. And you just do the same thing pretty much, but slam x in the middle. And remember that it's the complex conjugate of the wave function on the left and then the wave function on the right. In this case, that just combines to be the wave function squared. So I just kind of plug that in right here. As you can see, the complex conjugate of the wave function is just equal to the wave function, and the x is sandwiched in between. So that simplifies to the wave function squared. And then you have an x dx. And then if you plug that in the calculator, it just gives you 0. And that actually makes sense because here I drew a little picture of what this function would look like with an infinite square well, where the bottom here is the x-axis, so it goes from -2 to 2, and there's 0 in the middle. And this equation is just the 4 minus x squared. It's just a upside down parabola. And we know that's completely symmetric about the vertical axis. So if you want to find the expectation value, that's like finding the average of all positions. And that'll just be pretty much at the middle, which is 0. So this answer makes sense. Now moving on to question 3. So the answer to question 2 is 0. But now moving on to question 3, it's find the expectation value of x squared now. So you pretty much do the same thing as the last question. I pretty much have the same thing here. You have the wave function squared. But instead of x dx, it's x squared dx. And then once again, I just put this into my calculator, and then you get a non-zero value now, 0.571. Excuse me, sorry. So that's the answer to that, and that makes sense why it's not 0, because what you're doing is you have x squared. So if you look at the picture again, whenever you square x, whatever x value you choose, it can be anywhere between -2 and 2. If you choose a negative number, if you square it, it's obviously going to turn into a positive number. You do that over all, you find the average of that, of all x values, and then obviously you're going to get a positive non-zero number now, because squaring all the negatives, it'll always give you a positive number. So that's the answer to question 3. Now question 4 is find the uncertainty of x. And you do that with this formula. I'll show you in a sec. Again, you can just find this in the textbook. I think it's in chapter 2. The uncertainty delta x equals the square root of the expectation value of x squared minus the expectation value of x, and then you square that. And we already found that the expectation value of x is 0, and the expectation value of x squared is 0.571. We already found that. So then you just plug that in the equation. It's pretty simple. Square root of 0.571 minus 0 squared equals this value, 0.756. So that's the answer to question 4. Lastly, we have question 5. This is the last question. Find the expectation value of the momentum P. And so this is the third time. We already know, we're pretty much experts now. We know what formula to use. Integral from -2 to 2 of the wave function squared. But we have a P in the middle now. So that's kind of awkward, but what we know, you can find this in the textbook, is P can be represented as IH bar with the first derivative of x. So we have to plug that in. So that's what I did right here. And then, so you have the first derivative of x, so you solve that for the wave function, and then you get this value here. And then plug that back into the integral on the bottom, and then you just get 0 again. So that's the answer to question 5. And that makes sense conceptually because going back to the drawing, if you find the momentum at any of these spots, you can kind of imagine it as like maybe a particle. It's like moving back and forth. And there's some moments where it's moving to the left, but then there's equal as many moments where it's moving to the right. So left and right cancel out, and it gives you 0. And that's problem 2.8.